Uh, yeah, thanks for organizing this workshop and inviting me, giving me an excuse to come back to Israel after 5 years. Really glad to be here. So I want to tell you about this line of work that I have been involved in for the last, I guess, 2 to 3 years. And this is, joint work with many amazing people, including Umar and Siddhant, who are students at Berkeley, Tim and Peter, students at CMU, and Venkat, my colleague. So the title of the talk is the Kikuchi matrix method. And I'm using the word method in the same weak sense that Polya intended. Polya said that if an idea gives you a proof of a single theorem, it's a trick. But if you can prove at least 2 theorems with it, then it becomes a method. Okay, so that's my standard. I'll at least show you 2 applications. So I can use the method with impunity. So I'm going to explain this method in quite a bit detail throughout the talk, but at a very high level, just to begin with, the method is a way to reason about problems, about cycles in hypergraphs, by reducing them to questions about cycles in some graphs built from the hypergraphs. Okay, and these graphs I'm going to call Kikuchi graphs today. And it turns out that the cycle problems that arise on these Kikuchi graphs, they can be answered by studying spectral norms of certain matrices associated with the graph. So the whole machine then looks like, if you want to understand some hypergraph combinatorics problem, you somehow go through this machine and understand spectral norm of some matrix. Okay, that's the high-level spiel. A historical note before I go on with the talk: the name Kikuchi, that some of you might be wondering about, comes from the physicist Ryoichi Kikuchi. Ryoichi Kikuchi worked in statistical physics, and he considered a variant of beta free energy, if some of you have heard about it. That is now called the Kikuchi free energy. None of this, by the way, is relevant for the talk. But it turns out that it's a beautiful idea, and it leads to a construction of a matrix of the kind that's going to arise in my talk today. And this was first observed in a very cool paper of Alex Wine, Ahmad Alawi, and Chris Moore. So they are the ones who basically invented this particular matrix. Today I'm going to tell you how some new combinatorial properties of this matrix really help us do a lot more with it than just like this Gaussian tensor PCA business. Okay, good. All right, so let's begin. I'm going to tell you 3 applications of this method. First, I'm going to show you how this method yields a proof of a certain girth versus density trade-off that Feige had conjectured about 15 years ago. So you can use this method to confirm Feige's conjecture. In the second part of the talk, I'll tell you how the same method can be used to give algorithms for smooth versions of K-SAT problem, which are as good as the best known guarantees for random K-SAT. So somehow the same method can be used to show that smooth K-SAT is no harder than random K-SAT. And finally, in the last part of the talk, I'll use the same idea to prove a somewhat better lower bound on binary 3-query locally decodable codes. Okay, so they all look quite a bit different, and you might be a little bit, surprised how these are all somehow on the same slide. But you'll see that somehow there is a very simple inherent connection between all these 3 problems. Okay, good. So let's begin by looking at this first application. I really like this because it's a problem that can be described in 2 minutes, and you can reason about it. So let me tell you what this problem is. Okay. So this is a problem. It's an example of what goes by the name of Moore bounds, and at a very high level, these are trade-offs between length of the smallest cycle or girth and the density or the number of edges or size of the resulting object. Okay. So here's the simplest question of this type. Suppose I give you a graph on n vertices and n times d over 2 edges. That's like saying that the graph has average degree d. The question is, how large, subject to these constraints, can you make the length of the smallest cycle in the graph? Okay, so let's think about it together. If d equals 2, then you have like a graph on n vertices and n edges, and definitely the best thing you can do is just pick one giant cycle, making the girth as large as n. Okay, which is really the maximum it can be for a graph with any cycle, right? So the question is, what happens if d becomes bigger than 2? Okay, so it turns out, so this was like a famous conjecture of Bolobash, and it was confirmed in a theorem of Noga alone Shlomo Huri and Nati Lineal about 20 years ago, they showed that there is like a sharp phase transition in the extremal girth of a graph as the average degree rises from 2 to any constant bigger than 2. In fact, they proved very precisely that the girth of any graph with average degree d is no larger than 2 times log of n to the base d minus 1 plus 2. Okay? So for any d bigger than 2, this is the logarithmic bound. And this goes by the name of irregular Moore bound. In fact, this leading constant 2 in front of log n is subject of much research. We can reverse this inequality if we replace 2 by 4/3, and the high girth graphs turn out to be Ramanujan graphs, these Lubowski, Phillips, Sarnak expanders. But we know no better construction. So, that's an open question in this direction. But today, I'm going to be interested in hypergraph variants of the same problem. So I'm going to be interested in girth density trade-offs for 3 and more generally k uniform hypergraphs. Okay? Well, if I have to study this question, I have to first tell you what is a cycle in a hypergraph. So here's what I'm going to do. I'm going to take a very simple property of cycles in graphs, and then I will use it to generalize this idea and define cycles in hypergraphs. Now, I want to alert you right away that at first my definition might look a bit awkward, but I'll come back and justify to you why it's a very reasonable thing to study. Okay? So here is a property of cycle in graphs. I claim that a cycle is a subgraph where every vertex has even degree. So every vertex is touched an even number of times. Okay? In fact, this definition includes not just cycles but unions of cycles. But if you were to use it to define girth, then you would end up with the same value. Right? Because of course there is no gain that you get if you use unions of cycles. Good. Notice that this definition forgets the connectivity requirement, right? So it forgets this combinatorial idea that a cycle is supposed to be connected, but I'm going to be happy with it for now. Okay. I'm going to use this property to define a similar object in hypergraphs. Specifically, I'll say that a sub-hypergraph, a collection of hyperedges, is a cycle in the hypergraph if every vertex is touched an even number of times. Okay, so even number of hyperedges contain it. Good? So why might you care about this idea? So let me explain this very simple connection that might help you appreciate this notion. Think of a graph as describing two sparse linear equations modulo 2. So in edge ij, think of it as associated with an equation xi plus xj is 0 or 1 mod 2. Okay? Then a cycle in a graph is simply a linear dependency, right? Because if I take the equations corresponding to the edges in the cycle and add them up, then because every vertex is touched an even number of times, you get a cancellation, right? In fact, the girth of a graph in that sense is precisely the length of the smallest linear dependency in the set of equations that I have. And this connection continues to, of course, hold even for 3 uniform hypergraphs, just 2 sparse equations change to 3 sparse equations, okay? So in particular, because length of the smallest linear dependency corresponds to distance of the code, you have this basic connection that studying girth of these hypergraph problems relates to studying extremal rate versus distance trade-offs for LDPC codes, which are codes with with sparse rows or columns. Okay, so that's one reason to care about it. In the middle of the talk, I'll give you one more reason to care about it, but right now, hopefully, this is enough to keep you going. Okay, good. Any questions so far? Okay, good. So let's ask the question of trade-offs between girth and the number of edges in the hypergraph. Okay, so here is a trivial observation. Because of this connection to linear equations mod 2, I hope everybody sees that if I have n plus 1 equations in n variables, then they're going to be linearly dependent, and therefore there must be a cycle. And so that means that every hypergraph with at least n plus 1 hyperedges must have a cycle of length at most n. Okay, so that's going to be like one simple, trivial, extreme point in the trade-off, that if I have n edges or n plus 1 edges, then there is a cycle of length n. Now, in graphs, as soon as the average degree becomes like larger than 2, let's say like 2 plus epsilon, then there is a log n length cycle. So you can ask, what is the minimum number of edges required so that every hypergraph with that many edges has a log n length cycle or order log n length cycle? Okay. So this question was studied by Asaf and Jacques Verstraete, and some of the logarithmic factors were improved later by Feige. The conclusion of both these results is that if you take a k uniform hypergraph, with at least n to the k over 2 hyperedges, and I'm ignoring polylog factors, then there must be a log n length cycle in such a hypergraph. Okay? Now, let me plot this 2 points that we just discussed. Okay? You have one end n edges, n girth. On the other end, you have n to the k over 2 edges and order log n girth. Now, if you ignore constants, then these two thresholds are exactly the same for a graph. So there is no, large interesting regime in between. But if you consider 3 and 4 and, larger uniformity than 2 in general, then there is an interesting regime in between, and you can ask what happens there. So, you could imagine two possible worlds where there is like some midpoint where there's a sharp phase transition from like n to log n, or you could imagine some kind of a smooth interpolation, okay? And so this was the subject of conjecture that Feige made. Feige in fact said that there is a smooth interpolation between these lines, between these 2 points on the line. He said, suppose you have a graph with m, which is the number of edges, which is like n times n over l to the k over 2 minus 1. This looks like a mouthful, but it is simply a parameterization of the line I showed you on the previous slide with this single parameter l. So if you think about it, if you plug in l equals 1, then m becomes n to the k over 2, the right endpoint of the line. If you plug in l equals n, it becomes n, so it's the left endpoint of the line. Okay, so this single parameter l, as it grows from 1 through n, you basically progress, from right to left on the line I showed you on the previous slide. Okay, so Feige said that if you take a point parameterized by L, then there must be a L log n length cycle. And in particular, there are regimes where there is a root n length cycle, but no smaller, and n to the epsilon length cycle, and so on. So in some sense, there is a kind of smooth interpolation between these two extreme points. Okay, good. So Feige's motivations related to finding better algorithms for refuting random 3-sat, and I'll come to this, in the middle of the talk. But in the course of this investigation, he was able to verify this kind of a conjecture for random 3 uniform and k uniform hypergraphs in general. And in some sense, the conjecture is simply a statement that random hypergraphs are essentially extremal. That was the intuition Feige had. Good, yeah. So over the years, there is a little bit of work on trying to make progress on this conjecture. There is a paper of Noga and Uri Feige that gets a suboptimal trade-off for k equals 3. So you should have had n to the 1.5 over root of L according to the conjecture above. But you get n square over L for L log n length cycle. And there was a more general combinatorial approach for generalized girth problems that Feige developed in Tal Wagner's, Feige and Tal Wagner developed in Tal's, master's thesis. Good. So, I can now tell you the result. So basically, the first result, the first application of the Kikuchi matrix method is a confirmation of Feige's conjecture up to this extra log to the 2k n factor that, multiplies the density m. So if you give me, a little bit larger number of edges by factor log to the 2k of n, then the conjecture is true. Actually, very recently we found a simpler and tighter proof of the same theorem that actually tightens up these parameters and replaces this log to the 2k n slack with just a single log n slack. And if I have time at the end, I'll tell you what the single log n really amounts to. It's actually a very interesting quantity, and removing it, I think, is a very good question. One additional part that I like about the new proof is that it actually gives a new proof of even the classical irregular mode bound of Alon, Huri, and Lineal. So you get a spectral proof instead of a combinatorial one this time. Okay. Good. So that's basically the result for the first part. I can pause here and then continue and tell you how it's proven. Any questions so far? Okay. Good. So let's see how the Kikuchi matrix method works here. So let's say my goal is to prove that every 4 uniform hypergraph with n square over L hyperedges has a L log n length cycle. Okay, I just specialized this expression I had on the previous slide to 4 uniform hypergraphs. The reason I'm looking at 4 is because it's the smallest even number bigger than 2. Odd numbers turn out to be a little bit non-trivial in this context. So towards the end, I'll tell you how things generalize to odd, but I'll focus on even for most of the talk. Okay. N square over L. So remember that n to the k over 2, if you plug in k equals 4, is n square. So n square is the right end of the trade-off, and n square over L is basically the right way to parameterize the line I showed you on the a few slides ago. Okay. So that's basically my goal for the rest of the next 10 minutes. Okay. Good. So I told you that I'm going to, prove properties of hypergraphs by relating them to, issues about some graphs. So let me introduce this graph. Okay, let me introduce the so-called Kikuchi graph. So the Kikuchi graph is a parameterized family of graphs, one for each parameter L. Okay. The vertices of this graph are simply all possible subsets of size L of the original universe of the hypergraph. Okay. And two sets S and T are connected if the symmetric difference of S and T is an element of the hypergraph. So S and T simdiff out to some 4 tuple that lives in the hypergraph. Okay. Now notice I'm going to filibuster for the next minute to just make some random comments about it so that you have time to digest it. Okay. Here's one simple comment. Even though I have an object which is polynomial in n, I'm going to invoke this graph family for L, which is very large, root n, n to the epsilon, and so on. So this graph will be huge in general, it could be exponential sized, okay? And that's fine, okay? Here's a second comment. Imagine that you think of every element of the hypergraph as its indicator vector. So it's the 4 sparse Boolean vector, 0, 1 vector, okay? Now think about defining the Cayley graph on the whole hypercube with the elements of the hypergraph as generators, okay? Then the Kikuchi graph at level L is simply the projection of the Cayley graph to the level L of the hypercube. Okay, so it has this nice additive structure and it's going to be really important for us. Good? Any questions so far? That's the main object of the talk, so I want to make sure that this slide is actually absolutely clear. Good? Okay, very good. One more comment I'll make. This graph is very sparse in some sense, okay? So notice that, the edge occurs only when S and T symmetric difference out to an element of size 4 that lives in the hypergraph. And S and T are huge sets, they're L size sets, L can be root n. So in some sense, the only way they symmetric difference out to a set of size 4 is when they intersect in all but, 2 elements. So, it's a very sparse graph, compared to the size, okay? Good. All right. So that's the Kikuchi graph. So let's begin this project of relating cycles in the hypergraph to the cycles in Kikuchi graph. First, I want to claim that it's a very elementary observation but very important that cycles in this graph actually correspond to cycles in the original hypergraph. Okay. So let me make a precise claim. Instead of cycles, I'm going to look at closed walks. Sorry for not writing closed there. So my walks always loop back. And the walk, if you remember, it's just it's a cycle where I'm allowed to revisit vertices. Okay, so that's all I'm doing. It's convenient combinatorially speaking. So a closed walk in the Kikuchi graph. So it's a closed walk looks like go from set S1 to S2 to so on up to come back to S1, right? Now each edge involves a transition using some element of the hypergraph. So that's the one I've written on the top. Okay, so S1 to S2 goes through C1 and S2 to S3 goes to C2 and so on. Okay. So I want to claim that such a closed walk either corresponds to a cycle, as in some subset of C1 through CR actually includes a cycle of the type I'm interested in, or something else happens. Okay, and I'll fill in this something else as I do the proof. Okay, so let's see. Here's my very, very simple proof. I'm going to write down the conditions that S1, S2 transition occurs with C1, S2, S3 transition occurs with C2 and so on. Okay. So if I think of each of these sets as the 0, 1 indicator vectors, then I have that the addition mod 2 of S1 and S2 is C1, addition mod 2 of S2 and S3 is C2 and so on. Okay. Now notice that every set appears exactly twice on the left hand side, which means that if I add all the equations on the left hand side, I must get a 0 mod 2, which means that the CIs, the indicator vectors, must also add up to 0 mod 2. Okay. What does that mean? It means that every vertex appears in an even number of elements of the set C1 through CR. Okay. Now this is of course the definition of the cycle except for one little snag, which is that there is nothing that forces us to use distinct CIs. In fact, instead of a closed walk, even if my walk was a simple cycle, I could still use C1 or C2 multiple times because there are multiple transitions that use the same edge or the same hyperedge of the original hypergraph edge. So I could in general have a multiset C1 through CR, just that simply even number of times uses each C1 and C2 and so on, and by virtue of that basically cancel out. In that case, I will not get a cycle. Okay. So now let me define, this idea of an even returning cycle. It's basically the kind of walk that I don't like. Okay. So I'm going to say that a multi-set of hyperedges C1 through C2R is, an even returning cycle if basically the multiset, includes 2 copies or even number of copies in general of everything that appears in it. Okay. And so now, I can fill in the rest of the claim. So, every closed walk in the Kikuchi graph either contains a honest to goodness cycle inside it, or it must be even returning. Good? Okay, that's very simple. That's where the additive structure plays a role. And so now, I'll tell you the rest of the idea to prove, Feige's conjecture on, the existence of short cycles. I'm simply going to make 2 different counts. I'm going to count total walks of length 2r for some parameter r. I'm going to count all even returning walks of length 2r. And I'll prove to you that even returning walks are strictly smaller in number than all walks. Okay. If this is true, then there must be a walk that does not, even return and therefore contains a cycle. Okay. That's the... Yes, all my walks are closed walks. Sorry about that. I should have included the word closed. Good. Yeah. Okay. Any more questions? All right. Okay. So let's see. Okay. So I'm going to do both of these counting things by relating them to spectral norms of some matrices. Okay. That's the second idea, that I'm going to relate both these things by doing just some spectral norm computations on appropriate matrices. Okay. So let's do this. It's also very elementary. Let's first, relate the length 2r walks, all possible 2r length walks, to the spectral norm of some matrix. Okay. So in fact, I'm going to relate it to the spectral norm of the 0, 1 adjacency matrix of the Kikuchi graph. That's all. And the connection is very, very simple. If I want to count the walks of length 2r in the Kikuchi graph, it is simply trace of the 0, 1 adjacency matrix to the 2r. Okay, this is like a classical observation. That's all. That's really all there is. And the way I can and just in case you wanted to look at a proof of it, it just simply comes from expanding trace of k to the 2r as sum over closed walks, and then noticing that any term contributes only if all k's evaluate to 1, in which case there is an edge. Okay, good. So the second fact that plays a role in relating this to the spectral norm of the 0, 1 adjacency matrix is a simple observation that k to the 2r, the eigenvalues, this is a symmetric matrix, so the eigenvalues are just powers of the eigenvalues of k, and same with singular values. And so trace of k to the 2r is simply the sum of singular values of k to the 2r. And so one of them must simply be a lower bound. So sigma max of k to the 2r is a lower bound. Okay. So in particular, by taking any quadratic form of this matrix k, I can get a lower bound on number of 2r length walks in kh. And I'm simply going to use the all ones vector appropriately scaled. Okay, so it's all completely elementary program here. I just get a lower bound in terms of some scaled power of the number of edges because of the quadratic form I'm using. Okay, good. Sorry, what? Oh, it's a quadratic form raised to 2r. Is that the question? Yes. Sorry. Yeah. I should have some brackets there. Sorry. Okay. Good. Yeah. So let's do the other thing. Okay. It's also very simple. I will now relate the number of even returning walks of length 2r also to a matrix, but this time, for kicks, I'm going to use a random matrix. Okay. It will come in naturally now. So I'm going to take some appropriate signing, it's going to be a random signing of the Kikuchi graph, and show you that the expected trace of a high power of the signing of this matrix would actually relate to the number of even returning walks. Okay. It's also very simple, so let me do this explicitly. I'm going to introduce a uniformly random ±1 valued random variable for each element of the hypergraph. Okay. And now I'm going to construct the matrix where for an edge S1, S2 that goes via an element C of the hypergraph, I simply replace it by B sub C, the bit I sampled for that particular element of the hypergraph. Okay, that's it. So, the claim is that if I take such a signed Kikuchi matrix, then the number of even returning walks of length 2r in this Kikuchi graph is in fact equal to the expectation over the choice of B sub C's of trace of A to the 2r. Okay. And this again is a very simple observation. The exact same expansion I can write down. I can replace it by expectation of the product of the B sub ci's. And then now the only observation is that B sub ci's are mean zero random variables. So the only way a term contributes is if B sub ci, each of them is squared. So each of them appears an even number of times, in which case, I am exactly counting the even returning box. Okay, so very, very simple. Good. So, by the same kind of logic of relating traces of powers of matrices to, spectral norms, I can write down that trace of a to the 2r is at most the number of singular values times sigma max of a to the 2r. Okay, so capital N is the size of the matrix, so that's an upper bound I have. And so, I get an upper bound on the number of 2r length even returning box. Okay, good. So, I have this lower bound, I have this upper bound. For a given 2r, if I can somehow imagine that I can prove that sigma max of the signed Kikuchi matrix is, let's say, at most half of this, my estimate of the spectral norm of the unsigned matrix. Let's say I have a factor 2 gap between them. Then I get a factor 2 to the 2r gap between sigma max a to the 2r and, the sigma max of k. And if r is about log capital N, then this capital N factor that I have additionally in the upper bound can be cancelled out. Okay? So this is basically the relationship which gives me r, which is about log of capital N. Remember that N, the size of the matrix, is small n choose L. So log of capital N is about L log N, and that's the reason I actually can prove the existence of L log N length cycles. Okay? So the remaining thing is to prove an upper bound on the largest singular value of this signed Kikuchi matrix. Okay? Now let me tell you that you might have seen this kind of a signing before. Okay? In particular, these signings occur in understanding lifts of graphs. So for example, there is a program of constructing Ramanujan graph families by starting with like a constant size graph, which is Ramanujan, and then somehow constructing a signing which lifts it to a graph on twice the number of vertices. Okay? In that context, Bilou and Lineal, and actually later results, improve the parameters of the result a little bit better. They proved that if A is a random signing of any arbitrary d-regular graph, then the spectral norm of A with high probability is up to polylog factors root of d. Okay, and in this context, the all ones quadratic form, the unsigned matrix quadratic form, looks like d. So you actually get the kind of result we want. Okay, for d, which is the degree which is large enough. Okay, but this is for graphs, and it turns out that in our case the situation is a lot more subtle. Okay, notice that in the graphs, if you take a signing of a d-regular graph, you have about n times d random bits. Okay, where n is the number of vertices in the graph. So in some sense, you have space for doing union bound if you wanted to. Of course, the proofs don't go this way, but that's the rough intuition. In our case, the graphs are n to the L size, where L is root n, for example. So the graph is exponential sized, but the number of random bits is really like at most n square. So we are really in a much randomness starved setting. So our signing is not really random. In fact, it's far from it. It's a very correlated signing. And our goal is somehow to still prove a theorem of the kind of Bilou lineal. Okay, so that's roughly some sense of what we are trying to do. Good. But nevertheless, what we have done is reduce the proof of hypergraph more bound to establishing the spectral norm upper bound on signed Kikuchi matrices. Okay? So that's basically all I'm going to tell you right now on the proof of Figes conjecture. Towards the end, I'll tell you a little bit about how we actually establish a spectral norm bound. But what I'm going to do next is give you a similar arrow from refuting smooth k-sat formulas to again the same object, spectral norm of Kikuchi matrices. But before going that, I want to ask if there are any questions before I move on. Okay, I hope the silence means everything is clear. Yeah. Yeah.
Somehow if you're increasing the density, then you're hoping to get a shorter cycle.
Yes.
Can you say how increasing the density helps you in understanding this spectral norms? How does it affect things here?
So let me maybe say a sentence that might help. For a given density, I will actually use a correct member of this Kikuchi graph family to analyze. So roughly, the intuition is the following. if I want to prove that there is a L log n length cycle in a hypergraph, then I want to look at a graph whose size capital N satisfies this formula log of n is about small l log n. Does that make sense? So it's not like so like the way the density plays a role is like it really tells me which Kikuchi graph to work with. So the choice of like using the same parameter L to index both the Kikuchi graph and the density of the matrix was intentional. It is because they are really the same. Did I answer your question? Oh no. Oops. So oh yes. Well, I guess you need to repeat the question for me.
Because I understand that you use L both for the side of the Kikuchi matrix and for the length of the cycle, but it also comes into the density to hypergraph, right?
Yes.
So how happens here if you increase the density, you choose L to be smaller. Can you tell how somehow in analyzing the spectral norm of the Kikuchi matrix, the density of the hypergraph?
Okay. So let me see if I can summarize Shahar's question. I think the question is about like where in the proof of the spectrum upper bound would it show up that increasing the density of the hypergraph allows a shorter cycle to exist. Like somehow this part of the proof would capture this idea. I am going to hopefully have a slide on this, but let me say the following right away. What will turn out is that if you normalize correctly, the right Kikuchi graph that you pick is such that the minimum degree of the Kikuchi graph. Let me back up. Imagine that your hypergraph is random to begin with. For worst case hypergraphs, I had to do something else. But imagine that your hypergraph was random. In some sense, that's code for the simplest possible object of the type. Then you can prove that the right Kikuchi graph is such that the minimum degree of the Kikuchi graph is order 1. So I pick the member where the minimum and the maximum degrees are both about order 1. And that's, in some sense, like it turns out that wherever the degree becomes omega 1, the minimum degree becomes omega 1, I can actually establish a non-trivial spectral norm upper bound of the Kikuchi graph. Okay, but hopefully I'll tell you a little bit more in detail, but that's the rough intuition, okay? Good. So, all right, so let's see, this second part, I'm going to basically reduce it to the same problem, but the beginning, the problem is kind of different, okay? So, yeah.
That's already known, so you just want to go directly. That was already this original paper of
I'm going to discuss all of this. It's not true. So there is a gap between algorithms and certificates, and there's also a gap between strong refutation and weak refutation.
If you ignore those things, then you're already done.
Not really, because even 5AKM OFAC certificates require a combination of combinatorial and spectral certificates. So you still have to analyze some spectral certificates. Yeah, I think I'm coming to that part now. Okay, good. So let me discuss, how to answer Asaf's question now, okay? So let me discuss this problem of refuting CSPs, okay? So I'm going to think of it as an algorithmic problem where I'm given a k-sat formula phi with m clauses and n variables, okay? And the goal of the algorithm is to generate a value in the interval 0, 1 such that v is always a correct upper bound on the value of the input instance, meaning value by value I simply mean the maximum possible fraction of constraints satisfiable by any assignment, okay? Now, if this is all I demand of you, then of course this problem is very simple. You think of an algorithm that outputs 1 all the time and you win, okay? The reason this goal is interesting is because my success criteria for the algorithm are non-trivial. So I'm going to say that this algorithm succeeds in weakly refuting the input formula phi if the value that it outputs is strictly less than 1, okay? And the way to think about it is, combined with the correctness property, if v is less than 1, it means that the algorithm has produced for you a certificate of unsatisfiability of the input formula phi. Okay. More stringently, I would also care about strongly refuting the formula, where I not only want to prove that no assignment satisfies all the constraints, but in fact prove that every assignment must violate a constant fraction of constraints. And so, this is some formulation of finding certificates of unsatisfiability for input formulas. Okay, that's what this is. And you should think of it as the natural search problem for unsatisfiable formulas. I mean, if the formula is satisfiable, the natural search question is to find a satisfying assignment. If the formula is unsatisfiable, the natural search question arguably is to find a certificate of unsatisfiability. Okay. So what's our goal? Now, of course, by this connection, this problem is as hard as worst case KSAT. So, we might not hope for a greatest possible result in worst case. So our goal would be to, succeed in finding an algorithm that is efficient and succeeds in refuting, as broad a family of unsatisfiable instances as possible. Good? So what I'm going to do now is summarize what we know about this problem in two settings. First would be worst case KSAT formulas. And second would be, in some sense, the other extreme, the random KSAT formulas. And the punchline is going to be, which one is somehow a typical picture. Okay, so the question I'm going to be interested in is, which one should we believe as, in some sense, the right behavior of KSAT formulas? And in the context of this, we will define smooth KSAT formulas and study them. Okay, that's roughly what's coming up ahead. So let me summarize our knowledge of this problem for worst case KSAT. And again, I'm always going to look at strongly refuting KSAT formulas right now because, and somehow that is the cleaner setting I'm going to work in today. Okay. So in order to summarize the knowledge, I'm going to plot all known algorithmic results, and in fact also hardness results, on two axes. On the x-axis, I have the number of constraints. On the y-axis, I have the running time. And the reason for doing this is because the problem of finding certificates of unsatisfiability gets easier if you have, or at least intuitively gets easier if the number of constraints increase. Like somehow denser the formula, it should only in principle help you to find a certificate. Okay. So both these numbers I'm going to plot in log scale, meaning I'm only plotting the exponent of the number of variables n. Okay. So despite my saying that the problem is supposed to get easier as I increase the number of constraints, really nothing better than some kind of brute force search. I mean, you can shave off some constants is known until you hit number of constraints which is strictly larger than n to the k minus 1, which is factor small n short of the maximum n to the k. Then at n to the k you have a polynomial time algorithm, and there is this yellow line. It's not just an artist rendition, it's an actual straight line here. It turns out that in the log scale, the behavior of the best known algorithms running time, and as the density varies from n to the k minus 1 to n to the k, is indeed linear in this log scale. Okay, so that's the best known algorithm, and this whole picture is conjecturally tight if you assume the exponential time hypothesis. Okay, so that's basically what we know about worst case. I don't want you to remember anything except for the following 2 points: that there are two inflection points in this curve. One, the existence of sub-exponential time algorithms that seems to occur at anything bigger than n to the k minus 1. And then the existence of polynomial time algorithm that seems to occur as you cross this threshold of constant times n to the k. Okay, good. So now let me tell you a similar story for random KSAT formulas. Okay, so same kind of plot. And the summary of this whole picture is that the two inflection points exist even for random KSAT formulas, but they are shifted leftwards. So for random KSAT formulas, sub-exponential time algorithms start existing as soon as you hit any superlinear density. And there are polynomial time refutation algorithms, strong refutation, all my results are strong refutation, exist as soon as you hit n to the k over 2 constraints. Okay. So both those points exist, but they are shifted leftwards. N to the k is shifted to n to the k over 2. N to the k minus 1 is shifted to n. Good? It turns out that this n to the k over 2 is a natural breakpoint for, some kind of spectral algorithms. So some people tend to call it the spectral threshold. Okay? Good. And, just like before, this yellow line is indeed a straight line in this log scale that I'm plotting. Okay? Good. So, just to drive this point home, if I parameterize this yellow line with a parameter L, it actually says that there is an n to the O of L time algorithm that succeeds whenever the number of constraints is n times n over L to the k over 2 minus 1. And the reason I'm writing this down is because this expression should be familiar. It occurred in the first part of the talk, and it's not an accident. In fact, it will turn out that the existence of this, short cycles is very tightly related to the success of sub-exponential time refutation algorithms. So existence of polynomial size certificates, or these short cycles, actually relates very strongly to sub-exponential time refutations. This is somehow one of the main connections we are making here. Okay, but I'll come to this in a bit. Before I move on, I wanted to tell you one more curious result that's known in the context of random KSAT, and it's really one of a kind result in the sense that I literally know no other example of this. It's a very cool paper. So Feige, Kim, and Ofek proved that there is a point in this density curve strictly below this spectral threshold, so strictly, in fact, polynomially below this n to the k over 2 threshold, where short certificates of unsatisfiability exist. So there are polynomial size certificates that exist below this threshold, even though we don't know any polynomial time algorithm to find them so far. Okay, so for example, for 3SAT, this point happens to be n to the 1.4 as opposed to the spectral threshold of n to the 1.5. Okay, good. So you look at all of this and you might have this natural question: should I think of the conclusions about random KSAT as telling us something about KSAT or telling us something about the random model? And in some sense, the question is about whether the heuristics or the algorithms or the spectral methods that we are building in this whole line of work, are they somehow overfitting to the specific choice of the random model? Okay, so roughly based on this, intuition, Feige defined a significantly more general class of random models for KSAT, which he called smoothed KSAT model. Okay, so it's actually inspired by Spielman and Teng's work on linear programming, and this model is very simple. This time you start from an arbitrary worst case KSAT formula and you smoothen it. How do you smoothen it? You take every literal and perturb it randomly with some small constant probability, let's say 0.01. Okay, that's it. So notice that in the resulting formula, the number of the k-tuples that appear in a clause are worst case. There is no control over it. The only randomness comes from this random perturbation of literal patterns. Okay, does the model make sense? Okay, good. So just a small amount of independent perturbation of literals is enough to make any instance with like more than some 100n clauses unsatisfiable with high probability. So the refutation problem will make sense. Okay, so that's going to be our problem. That's the question that Feige asked. And really, like the intent of this question is this model somehow closer to the worst case picture, or is it more like the random picture? Like somehow where in the scheme of things is this model sitting? Okay, so the main result of this work is this picture, which is basically the same picture I showed you for random KSAT. So the main result is really saying that the behavior of algorithms for smooth KSAT formulas is really as good as the best known results for random KSAT formulas. So smooth KSAT formulas, in fact, are no harder than random KSAT formulas as far as we know. Okay, that's the result. And so, sorry about the messiness in the slides. PPTs don't transfer well. In terms of prior work, just to tell you the context of this work, the same trade-off was known for random KSAT formulas like I showed you earlier. For smooth 3SAT, there was an algorithm in this original work of Uri that proposed this model that succeeded in weakly refuting such formulas. I think this is the result that Asaf was pointing at, whenever you have at least n to the 1.5 constraints. Okay, but because it combines combinatorial and spectral certificates, it turns out that this idea is somehow more limited than the best known algorithms for random KSAT. So in particular, this idea does not seem to extend to 4 CSPs, like 4SAT, for example, or give strong refutation results even for 3SAT. Somehow both of those are somehow stuck because our techniques seem to be very different from random KSAT. Okay, so this whole picture really began in this joint work with Jackson Abascal, our student at CMU, where we basically discovered the green part of this curve. So we discovered an algorithm that strongly refutes KSAT for every k in the smoothed world, whenever the number of constraints is at least n to the k over 2. And then, in this work that I'm actually talking about right now, in the context of this Kikuchi matrix, we only discovered this yellow part of the curve. Okay, so usually, when I talk about sub-exponential time algorithms, I often, at this point, pause and apologize. It's like, yeah, it's a sub-exponential algorithm, maybe it doesn't impress you, it's not polynomial time. This time I'm quite happy because this yellow curve really relates to resolving the hypergraph more bound. And the next slide tells you one more application of actually proving this yellow curve. So this time, I have to apologize a little bit less for being interested in sub-exponential time algorithms. So coming to it, I told you this result of Feige-Kieman effect that shows that random k-SAT formulas have refutation witnesses below the spectral threshold. It turns out that the same result, so we prove the same result for smooth k-SAT formulas. Okay, so the exact same phenomenon with the exact same thresholds actually now holds for smooth k-SAT formulas. So even this existence of short certificates phenomenon is actually considerably more general than random k-SAT formulas. And the key ingredient here is really, the hypergraph more bound that I showed you in the first part of the talk. This is also the connection I think Asaf was referring to. So, I won't get into the I won't get into the details of how this connection works, but I'll just going to leave it at that for the purpose of this talk. Okay, good. So, what I want to tell you now is, how all of these results actually also arise by, relating it to the Kikuchi matrices and the signings of Kikuchi matrices in particular. Okay, good. All right. So let's do it. So let me first tell you the high level plan, okay, and then focus on one key part and then be done with it, okay? So it's going to be fairly short, much shorter than the previous part. So first of all, it turns out that by some standard tricks that Uri already knew 20 years ago, it's okay to focus not on k-SAT but on k-XOR. Okay, so it's okay to focus on just k-XOR formulas, which is what I'm going to do. It in fact turns out that smooth model is reducible, in the way we are doing these things, to just semi-random k-XOR instances. What that means is that, remember in the smooth model, I am flipping the literals with only 0.01 probability. Imagine flipping them with probability half. Okay, that's a semi-random model. So it turns out that focusing on this, more benign model is actually okay because we can do some kind of a reduction. Okay, so I'm going to only focus on semi-random k-XOR formulas. I'm going to show you, this is the only part I'll do in fact today, to show you how the signed Kikuchi graphs and analyzing them yields a simpler algorithm for refuting random k-XOR formulas. And the benefit of this simplicity is that we can go back and understand what was it about the random k-XOR formulas that makes this whole method succeed. And so by looking at this, we can extract a combinatorial property of random hypergraphs, a very limited combinatorial property of random hypergraphs that somehow plays a role. It in fact is quite related to Shahar's notion of small spread in the context of the sunflower lemma. So it turns out that we can define this notion of regularity of hypergraphs, and that plays a role here. And then, the rest of the proof proceeds by giving a decomposition of arbitrary hypergraphs into regular hypergraphs of same or smaller arity. Okay, and then basically we apply this result to, each of these pieces separately. That's the whole structure of the proof. But today I'm only going to tell you, how the signed Kikuchi matrices play a role in random k-XOR refutation. Okay, good. All right, so that's going to be my goal for the next 5 minutes, to tell you how you can refute random 4XOR formulas with, let's start with first n square constraint. So this is like the rightmost endpoint of this curve that we'll be looking at. This is the point at which you should expect polynomial time refutation algorithms. Okay, so I'm going to tell you how to do this with Kikuchi matrices. Okay, in fact, this time the Kikuchi matrix will be really simple. So it's, just some spectral refutation, as you'll see. Okay, good. So this is a reminder for what a 4XOR system looks like. My variables are, let's say, plus minus, my variables will be plus minus 1 valued, and there are n of them. And my constraints, because I'm in this plus minus 1 basis, they simply look like monomial constraints. I have many 4 tuples. For each 4 tuple, I have a constraint that says x1, x2, x3, x4 is plus or minus 1. And notice that I'm working with random 4XOR formulas, which means that each 4 tuple that appears in the system is chosen at random. And the right hand side for the equation is also chosen independently and uniformly at random. Okay, good. All right, so an instance of this 4XOR formula then is described by describing a 4 uniform hypergraph H of the 4 tuples that appear and the system of right hand sides B sub C's. Okay, now given such an instance, I can define the following homogeneous quartic polynomial. Okay, this polynomial multiplies the right hand side of a monomial constraint with the monomial that appears. Notice that, if x is a satisfying assignment for a given constraint, then each such term contributes a +1. And if it unsatisfies, like does not satisfy a constraint, then the corresponding term contributes a -1. This polynomial simply averages its plus or minus 1 terms. So you can think of it as computing the advantage over half of a given assignment x. Okay? And now, given that this polynomial computes the advantage over half, in order to strongly refute random 4 XOR formulas, it's enough to produce a certificate that phi x is at most some arbitrarily tiny constant epsilon as x varies over all possible assignments. Okay, is this reasonable? Okay, very good. So that's going to be my goal. So here is the idea, and this idea in fact goes back again 20 years to this work of Gert and Krivlevich. As usual, Gert and Krivlevich did this for 4 XOR and even arity XOR in 2001, and it took I think 2 additional years to get to the odd arity case, which has always been the game in this line of work. So here is what they observed, that this quartic polynomial phi x can be written as a quadratic form of some matrix. Okay, so what matrix? It's a very, very simple matrix this time. I have a matrix indexed by pairs of variables on rows and columns, and at ijkl, I write down the right hand side of the monomial constraint corresponding to I, j, k, and l if it exists. If it doesn't exist, I write down a 0. That's the matrix. Okay, and here is the observation that Gert and Krivlevich made. They said phi x is actually the quadratic form of this matrix K on the vector at any assignment x that populates the degree 2 monomials in x. So x circle 2 simply is an n choose 2-dimensional vector, which the entry at I comma j is simply xi times xj. Okay, so this is like a simple syntactical verification thingy, and the 1/6 is simply because every 4 tuple occurs like in 6 different ways. Okay, so up to a scaling, this is simply a quadratic form of x circle 2 on k, and I can give a very simple upper bound on this. This is upper bounded by the L2 square norm of x circle 2 times sigma max of k, the largest singular value of the matrix k. Notice that x circle 2 is a vector of plus minus 1s because x is a vector of plus minus 1s. So x circle 2's L2 norm is simply square root of n choose 2. It does not depend on x at all. So I have an upper bound that simply manages to remove the dependence on x and only depends on the largest singular value of k. In particular, if I claim an upper bound of this sort, you can verify it easily by simply computing the largest singular value of the matrix k. So this is efficient refutation as long as this bound is enough to give me a small value on the polynomial phi x. Okay. The only question is, when is sigma max of k small enough that I get a refutation? Okay. Good. So it turns out that as long as m is at least n square, the question of analyzing the spectral norm of k is a simple random matrix question, and really any reasonable method you throw at this problem actually works. So you can apply matrix Chernoff, you can apply trace method, whatever. Any method actually works, and they all work to actually give a good bound on sigma max of k, and you basically go home with the result. Okay, good. So now let's say we want to do the same thing, but now at a much lower density. So this previous simple matrix worked when m was at least n square. But now I want to do it when m is about n square over L, but L is usually super constant. Okay. So I want to in particular get an n to the O of L time algorithm to find a refutation whenever m is about n square over L. Okay. So this result for random 4 XOR was first proven in this work of Raghavendra Rao and Shram that I showed you earlier. And they used the matrix, which is a bit complicated, so I'm just going to give it a random name. I'm going to call it the symmetrized tensor power matrix for people who can associate something to that word. It's okay if you don't. It's a complicated matrix. It roughly corresponds to some matrix whose quadratic form is some power of phi x instead of phi x itself. And they analyzed this matrix with like some heroic, combinatorics. It ran into like 20 plus pages from what I remember. The downside of that for us is that it's a fairly technical proof even for random hypergraphs. So I don't know how to somehow take it and extend it to, arbitrary hypergraphs, etc., that I'm interested in today. Okay. In fact, just for random hypergraphs, a couple of papers have eventually tried to simplify the proof, and they succeeded for even k. Again, this even versus odd difference plays a role here. For odd k, even like the simplifications don't seem to work. Okay. So now I'm going to tell you how the Kikuchi matrix swoops in and like makes it all pretty easy. Okay. So the only observation is that this polynomial phi x, not a power of it, just phi x itself, is a quadratic form of n choose L by n choose L Kikuchi matrix. Okay, that's basically all there is to it. So remember the Kikuchi matrix. If I have a hypergraph with a single edge C, then the Kikuchi matrix is simply, indexed by sets of size L, and there is an entry at S comma T if S delta T is C. I'm going to call the matrix AC, which basically for every edge writes down the right hand side B sub C of that edge. Okay, and C is a constraint that appears in my 4 XOR system. Then the matrix A, which is the sum of A sub C's, and this is basically the Kikuchi matrix of my 4 XOR instance. Notice that this is exactly the same kind of object we analyze in the context of hypergraph mode bound. There we toss these B sub C coins ourselves. Here they were given to us as an input in terms of this random 4 XOR formula, but the underlying object is exactly the same. Okay, it's basically a random signing of the Kikuchi graph. Okay. Okay, once I have that, confirming that space is a quadratic form is really a calculation. The only reason I'm writing this down is to show you that there is a very short proof. You don't have to read it, okay? So phi x basically can be verified to be a quadratic form of this matrix. And once you do that, you can basically get a spectral upper bound. Yeah. Oh, A sub C is a signed matrix by itself. So yes. Yeah, it is A sub C is equal to B sub C times K sub C. Good. So now, I can do the same spectral upper bound just like before. Exactly, everything just works out just as before. Actually, one thing I should have observed, phi x is a quadratic form of this matrix, but on the vector of L-wise monomials in X this time, not pairwise monomials. Now, just to make sure that things are not confusing, my underlying polynomial phi x is still a quartic polynomial, even though the quadratic form is on L-wise monomials. Like somehow the structure of the Kikuchi matrix cancels out every monomial which is larger than 4. Okay, that's just how it is. Good. All right. So, long story short, we have reduced our problem to yet another time understanding, the spectral norm of the signed Kikuchi matrix. Okay. Good. So that was my second part. I have not told you how to do this for like non-random hypergraphs yet. I'll come to that in the last, couple of minutes. But now I want to go to the third application of Kikuchi matrix method. But before that, I can pause and see if there are any questions. Okay, once again, I hope the silence means everything is clear. Okay, so I want to tell you completely different things now. I'm going to tell you about locally decodable codes. So if I lost you in some of the technicalities in the previous few slides, it's time to wake up because this is completely different. Okay, so I'm going to tell you about locally decodable codes. So some of you might have seen this object before. Locally decodable code is an error correcting code that in my world takes k-bit message and transforms it into an n-bit code word. Okay, I'm only going to be interested in binary codes today. So, both my messages and the code word symbols are 0 or 1. Okay. I say that such an error correcting code is a q, epsilon, delta LDC if the following properties hold. First of all, it has a constant distance. So think of delta as some constant. It's a good code. It has constant distance. It can help you, correct constant fraction of errors. Okay. In addition, it has the local decodability property. That means that if I want to decode any single bit of the message, then in the received corrupted code word, I can read just q positions. This would be randomly chosen in general, but I can read any some q positions carefully chosen and apply some decoding predicate to it with a guarantee that whatever I learn would be, with some good chance equal to the bit that I'm interested in decoding. Okay, so that's the local decodability property, that any bit of the message can be decoded by reading just q bits of the received corrupted code word. Good. All right. So the main question, and these arise, for this audience, perhaps I don't have to discuss too much, but these arise all over. They were already somehow implicit in this earliest works on PCP theorem, and they of course have also applications to private information retrieval and worst case to average case reductions and so on. And the key question that we are interested in is understanding the best rate versus distance trade-offs for such QLDCs. Okay, so what is the best rate versus distance trade-offs we can get if I want my code to have constant distance and Q query local decodability? Okay, let me tell you what is known about this problem. So even though these codes were implicit in this earliest works on PCP theorem, they were formalized in this work of Katz and Trevisan, and some quick succession of works around the time basically settled the case of Q equals 2. So if I want a 2-query locally decodable code, the Hadamard code actually functions perfectly fine. The Hadamard code is kind of notoriously bad in terms of its rate, in the sense that the block length of the code becomes exponential in the message length. But it turns out that this is as good as it gets because we can prove essentially matching lower bound. Okay, so the case of Q equals 2 is basically settled. So now you can ask, okay, what about the next case? What about 3 queries? And here we already hit like things where we understand basically at some abysmal level, like we are very bad at understanding even 3-query locally decodable codes. So the same work of Carnegie and DeWolf that discussed this 2-query case proved that the block length of a 2-query locally decodable code with a constant distance needs to be at least quadratic in the message length. Okay, so these polylog factors were removed. I guess some of them were removed a few years down the line, but basically the bottom line is some kind of a quadratic lower bound here. Okay. On the other hand, the best known upper bounds are these breakthrough results of Yakhanin and then Efremenko. They show that actually you can truly beat the Hadamard code. You can get a truly sub-exponential block length, but still very, very far from our lower bound. So there's a huge gap here, and of course it's controversial which way the right answer goes. For larger query case, there is some bound that we can prove that basically generalizes this quadratic bound for all even queues. And for odd queues, basically our bounds are obtained by going to the next higher even queue. Okay, so I don't recommend understanding these expressions if you've not seen them before. Just remember this idea that the answer for odd queues is obtained by just going to the next higher even queue. That's basically how these lower bounds are obtained. Okay, good. So I can tell you what Kikuchi does here. So Kikuchi does a modest improvement to this quadratic lower bound of Carnegie and DeWolf. We can now prove a cubic lower bound up to some polylog factors from a quadratic lower bound. That's all. Okay, that's what we can do. We are of course very, very far from the upper bound, but the reason I like this result, of course it's my result so I should like it, but the reason I like it more generally is because it makes this new connection to semi-random refutation of XOR, and I kind of feel like there is more to it. Like we were able to extract this cubic lower bound, but my hope is that we should be able to extract more stronger lower bounds from this same machine, and I don't know, who knows, maybe even a construction. Okay, good. So all right, so that's the result, and in the next 5 minutes, I want to tell you just this connection to semi-random KXOR. That's all my goal is for this part of the talk. Okay, good. So here is basically the proof plan. I'm going to relate 3-query LDC lower bound. This would be a lossless reduction, by the way. It's a very simple and no loss reduction to proving that a certain semi-random 3 XOR formula is unsatisfiable. Okay, so I'm going to take a purported construction of a QLDC and form a 3 XOR formula, and the construction would be an LDC if and only if this formula is somehow satisfiable. So if I were to prove that this formula is unsatisfiable, it would establish that there is no Q-query LDC. Okay, and I will then, so even though I have like a randomish looking 3 XOR formula, which hopefully I should be able to prove unsatisfiability of by some vanilla methods, it turns out the only known method I know is to actually produce a spectral certificate of its unsatisfiability. And the spectral certificate basically uses the Kikuchi matrix. That's the whole connection. Okay, so let me just explain this first if and only if, and that will be it. Okay, good. Oh, and I should mention that these semi-random 3 XOR formulas are actually even more randomness starved than the semi-random formula I showed you before. Prior, like in the second part of the talk, the formulas had about 1 bit of randomness per constraint. This time I'll actually have only 1 bit of randomness per n constraints. So it's like even less randomness, but somehow it turns out that these methods are robust enough that they actually work even for these less randomness semi-random formulas. Okay, good. So think about, this is just like, some setup now. Think about what a decoder might want to do if you want to actually have this property of local decodability. So to decode a bit I, the decoder has some list of some query sets, some q tuples of coordinates that it will query. And in general, you can, without loss of generality, assume that the decoder would just pick a query set uniformly at random from this set of possible query sets it has for a given bit, and then just, apply the predicate it has in mind. And the reason this kind of thing is necessary is because, the corrupted code word has errors, and of course, I don't know where the errors are. So I need to have some randomness in my query sets so that I escape, this erroneous points in the received word. In fact, you can use this same logic to conclude, with some only minor loss in parameters, that the query sets in fact must be disjoint. So they must form a matching. Okay, so this is again like a completely black box thing. It only like changes the parameters by constants. Okay, so in other words, I can assume that the query sets of any locally decodable code look like basically a set of a matching for each particular bit I want to decode. So for the first bit, I have some matching. For the second bit, I have some matching, and so on. Okay, that's how my query sets look like. And because I'm interested in 3 query codes, these matchings are 3 uniform. Okay, good. It turns out that the distance of the code, because I want the distance to be constant, it translates into the condition that each of these matchings has basically omega n hyperedges. So it's like basically, almost perfect matchings. Okay, good. And you can ask, when does a given set of k matchings like this correspond to a locally decodable code? Okay, this also has a very explicit condition. A collection of matchings, let's first look at linear locally decodable codes. By that I mean that, the decoder simply takes the query sets and XORs them. Imagine like this very simple linear decoder. Let's understand when a given set of query sets like this give you a linear LDC. Okay, so I claim that any such query sets give you a linear LDC if the following holds. For all possible values of the k-bit message, I should basically be able to take any query set. There should be a code word X for any b-bit message, such that if I take any query set for any ith bit, then the XOR of those 3 bits basically gives me the ith bit bi. So basically, the condition simply says that I should succeed in locally decoding. Okay, that's all it says. Okay, so notice that the existence of such an X for a given b is a system of linear equations mod 2. Okay, so I'm writing down some XOR equations here. Okay, so in particular, and if instead of linear LDCs you had an LDC that applies a different predicate, then instead of the XOR I just apply that predicate p. So it doesn't change much. Okay, so now I can actually give you this reduction very simply. A collection of k hypergraph matchings of omega n size can possibly give me a q query LDC if the following family of XOR systems is satisfiable. This XOR families is 1 for every possible value of the k-bit message. So there are 2 to the k XOR instances here. Okay, for each b I define the following formula. My variables are the code word bits, and my constraints simply say that linear decoding succeeds. So for linear LDCs, this should basically be obvious why this is a reasonable thing to do. For non-linear LDCs also it turns out to be reasonable. In fact, you can prove that there is no linear LDC if the value of this XOR instance is significantly less than 1. So like it's unsatisfiable. And in fact, you can prove that there is no non-linear LDC, just like linear or non-linear, if the value of the same XOR formula is small enough. Like, instead of just less than 1, something like 2 to the minus q. And this comes from like some basic Fourier analysis, so nothing very complicated happens here. The message is that it's enough to prove that this XOR, like at least one of the 2 to the k different XOR formulas I defined, has a value which is very small, like 2 to the minus q. Okay? Did that make sense? Good. So, now I can complete the whole program. Which B would I use? So, here's the whole proof idea. I fix a collection of H1 through Hk, this hypergraph matchings. I define this collection of 2 to the k different formulas, and I will prove, or at least the proof works by showing that a randomly picked formula out of this set of 2 to the k in fact can be refuted. So the randomness is only in choosing this k-bit message here. Okay, so that's the only like semi-random part in this set of formulas. Okay, good. So yeah, I think this is basically the last part of the arrow. Good. So yeah, I guess I've explained to you this connection to various notions of signed Kikuchi matrices and understanding the spectral norm for these 3 applications. What I want to do in the last, I guess, 5 minutes, 3 minutes. Okay, good. Let's completely ignore the proof details. These slides, weren't very understandable anyway. So let's just summarize. Okay, so I told you like 3 possible applications: the confirmation of Fige's conjecture, refuting smooth k-set formulas, and proving a better lower bound on 3 query LDCs. And really, the main takeaway is that for this linear algebraic notion of cycles, it somehow seems like these Kikuchi matrices are powerful. So it might be useful in your application if you have some problem like this in mind. Okay, so I want to just end with like some list of open directions because I'm quite excited about this area right now. The first is like the obvious one, which is how do you prove tight bound for Fige's conjecture? So I told you like last we know is a bound which is off by a log n factor, and usually I'm okay with log n's, but this feels like too basic a combinatorial question to lose log n's on. So, for this particular question, I would be very interested in removing the log n. So we have some ongoing work with Benny and his student David Correa, along with like this group that we had a simplification with. So far, we have some ideas on how this could be done, but of course, proof evades us. There is also, this natural question of finding extremal hypergraphs that achieve, these Girth density trade-offs. So, what if at all is a hypergraph? There is some little space between random hypergraphs and the parameters, and you could ask, can you produce a higher girth graph than random hypergraphs? Now, such a question, corresponds to, constructing some high girth Ramanujan families in the context of graphs. You can ask, what is such an analogous family for hypergraphs? And we have no idea so far. So, that's a natural couple of directions in combinatorics. It also turns out that there is a, thin, and I will not explain it further, but if some of you know this matrix Spencer problem, and in general this issue of removing the square root log n's that arise in the application of Chernoff bounds and their matrix analogs, then this last log n is really, the matrix Bernstein root log n. And so it relates to this issue of, how you can or when you can improve the matrix Bernstein inequality. If this comment is not understandable, feel free to ignore. It's not that important. Okay. This is my favorite open question. Actually, this is Uri Fige's favorite open question too. This is the reason actually he defined conjecture like, which is, can you beat the spectral threshold for refuting random 3-set formulas? Okay. So I told you that the best known algorithms work when we have at least n to the 1.5 constraints. This question asks, can you do it with little of n to the 1.5 constraints? Now this question has been around for 15 years. In fact, Uri was trying to solve it 15 years ago. The reason I believe we have some new angle here is because it turns out that there's a reduction to algorithmically finding short cycles. So we showed the existence of short cycles in hypergraphs, but if you could algorithmically find them efficiently, you will actually achieve this result. Even this was known 15 years ago. The new insight we have is this connection to a graph problem. So now we know that these cycles correspond to cycles in these Kikuchi graphs. These Kikuchi graphs are implicitly defined in terms of the input hypergraph. The question is, can you somehow use this implicit description to algorithmically discover this cycle? I don't know, but it would be really cool if you could do it. Okay. I showed you this FKO result that shows existence of short certificates below the spectral threshold. Again, people have tried very hard, and we don't know any idea on how to go beyond this. It would be really great to do that. And finally, it's an open-ended question. Is the spectral double counting on Kikuchi graphs useful for other problems in combinatorics? I would, of course, be very interested in doing that. That's all. Thank you. Good. So the question is, does it follow from whatever I showed that linear LDCs are just as powerful as non-linear LDCs? I think this is classical. I don't think this is. Right. So, okay. So let me maybe mention this. Okay, let me maybe go to it. So Carnegie and DeWolf also at the heart of it are proving a spectral norm upper bound, but they found it more natural to do it in this quantum language. I should have mentioned that actually, you can recover all these old lower bounds in this new way. We just managed to improve it for 3 queries, but we can match all the known lower bounds via this, connection. And in this connection, it is really, in some sense, a one-liner that linear and nonlinear really can't change the parameters except for by constants. So you can change the block length by a constant, you can change the distance by a constant, but if you're not worried about the constants, then yes, there is no power to be had with nonlinearity. Excellent question. Yes. So I told you that the best known lower bounds for odd queries really come by going to one higher even query. So all we are doing for 3 queries is we are escaping this barrier. We are proving a lower bound which is truly correct for Q without going to 4. Now Amir's question is, can you do the same for 5? I don't know. So we've tried, and somehow these methods that we have actually have a combinatorial bottleneck. It doesn't seem to work for 5 or 7 or something. We have some ideas. Maybe in a couple of months I'll know how to do a little bit better, but yeah, right now I don't know. So maybe let me mention this one thing that I was going to say in the couple of slides that I skipped over. So it turns out that what we really use is a weighted variant. This was a little bit of cheating that I did for presentation purposes. So it turns out that the tightest parameters are obtained by reweighted Kikuchi matrices, which do have not just but also like weight. But in general, if you're asking like what might be the value of studying weighted Kikuchi matrices, so actually they arise quite naturally in polynomial optimization. Like in some sense, in XOR systems, the weights are naturally 0 or 1. But you could start with like a weighted polynomial optimization problem, and then you naturally arrive at weighted Kikuchi matrices. So certainly they are interesting objects to study.